Welcome to this explainer. Today, we're unpacking a massive, kinda shocking flaw buried deep inside modern AI hardware. But don't worry, we're also going to look at the brilliant engineering paradigm shift that's poised to fix it. Look, if you rely on digital systems for anything important, which, let's be real, is all of us at this point, you're absolutely going to want to hear this.
So, think about this for a second. Imagine walking into your bank, handing over your life savings, and they use a gambler at a roulette wheel to count your money. Sounds completely absurd, right? No way you'd accept that. But as we dive into the source material today, you're going to see why that is essentially exactly how modern AI operates down at the hardware level.
Section 1. The illusion of precision, why AI hallucinates at the hardware level.
We all kind of naturally assume computers are these flawless, perfect math machines. But the reality? It's much messier. The source material describes modern large language models, or LLMs, as massive, incredible encyclopedias. But fundamentally, they're what's called lossy environments. They compress vast amounts of knowledge using statistical methods, not strict reproducible ones. It's kind of like taking a picture of the entire world with a fisheye lens. You capture everything, but nothing is perfectly in focus. Or think of it like an old-school fax machine. It gets the general shape across, for sure, but you completely lose the crisp, perfectly reproducible details.
And here's the hidden hardware culprit behind this whole lack of focus: the FPU bottleneck. Modern AI relies really heavily on floating point units, or FPUs. But here's the kicker: an FPU doesn't do absolute math, it approximates. The sources describe this rounding not just as a tiny glitch, but as something that defines the entire system. It acts like a data mixer. Actually, scratch that. The source specifically calls it a wood chipper, churning out approximations that literally destroy forensic traceability. Once the data goes through, you simply cannot work backward to see exactly how a calculation was made. The receipt is just gone.
Moving on to Section 2, Gamblers versus Surveyors, the hardware battle for absolute truth. To really wrap our heads around this hardware bottleneck, there's this brilliant metaphor from the source material about how computer chips process reality. Quote, "The FPU is a gambler, the ALU is a surveyor." This was a massive aha moment for me. Inside our computer processors, the floating point unit is quite literally throwing darts to approximate an answer. But the ALU, the arithmetic logic unit, that deals only in absolute surveyor-like realities. In the ALU, 1 plus 1 exactly equals 2, every single time, no exceptions. So it really boils down to this core conflict. On one side, you have the chaotic gambler, guessing, approximating, running on non-deterministic logic. On the other side, the sharp, precise surveyor, absolute deterministic rules. The sources make a really powerful point here. You simply cannot achieve a verifiable digital receipt when your underlying engine is acting like a gambler pulling a slot machine lever instead of a reliable witness. If high-stakes decisions are on the line, you absolutely need a surveyor.
Now get this, because this blew my mind. Did you know different computer chips technically disagree on basic math? It's true. Adding to the chaos, chip manufacturers burn hidden proprietary seed tables directly into the silicon itself. That means the square root of 2 calculated on an Intel chip might be fractionally different from the exact same calculation on an ARM chip. It creates this hidden liquid foundation that totally lacks transparency. Independent verification across different machines? Practically impossible.
Section 3. The fax machine blueprint, forcing lossy AI to write lossless rules.
Okay, so we've got a gambler that can't even agree with other gamblers. How on earth do we extract perfect precision from this inherently unpredictable machine? Well, we build a completely new engineering paradigm. We don't just throw the AI away, that'd be crazy. Instead, we use the lossy, unpredictable LLM, our fax machine, purely as a translator. We prompt it, and it generates a perfectly deterministic virtual blueprint, formatting it into strict, unambiguous text, like LaTeX or C code. Then finally, we upload that blueprint straight into the strict rule-based ALU for execution. We're literally using the lossy system to write the lossless rules.
This whole process relies on what the sources call the von Neumann separation. By isolating the massive, lossy database, the statistical weights and pre-cleared copyright data of the AI, from the strict, deterministic instructions executing the code, we prevent the chaos from spreading.
We cleanly separate the statistical spaghettification of the AI's data from the absolute, surveyor-like reality of the hardware execution.
Section 4. Forensic traceability matters. Why high-stakes computing needs an undeniable receipt.
So why does all this actually matter to you and I? Real-world applications. When we're talking about high-liability fields, legal, engineering, financial ledgers, medical equipment, flight systems, we absolutely cannot accept a gambler. We need fully forensic traceable computing, where every single action leaves an undeniable digital receipt. If a critical system fails, we must be able to work backward and see exactly why, without that FPU wood chipper having destroyed all the evidence.
The source material refers to this approach as an evidentiary dream, and honestly, they've hit the nail on the head. Now, sure, the initial setup of this ALU surveyor method might cost a tiny bit more compute time upfront, but the payoff? It generates a universal, perfectly shareable truth. It totally prevents what the speakers called the liquidation of contributors' efforts, effectively ending the computational prisoner's dilemma, where non-deterministic methods are just stuck in their own isolated, unshareable logic.
Furthermore, stepping away from the isolated proprietary logic of FPUs gives us predictable parameters. By replacing the rigid guessing of the FPU with pure mathematical determinism, you can dial in exactly how much precision you need based on the time you have. It creates a perfectly accountable ledger of digital events. For the first time, we know exactly what the system is doing every single step of the way.
And that leaves us with one absolutely critical question to ponder. As we continue to offload more and more of our lives onto machines, our finances, our legal frameworks, our physical safety, what standard of accountability are we actually willing to accept? In the future of high-stakes computing, will you settle for the gambler's guess, or will you demand the surveyor's perfectly traceable blueprint? Thanks so much for joining me for this explainer. Keep questioning the systems you rely on, and until next time, keep learning.